Another piece to the valence bond theory, or the VB theory, is to actually describe how the covalent the covalent bonds are formed by the overlapping of the different orbitals. So if you haven't done so already, you probably want to look at the narrated PowerPoint files for the geometries and for the hybridization, and then come and look at this one, because I'm going to use terminology from those previous two examples in order to discuss then the physical manifestation of the covalent bonds, of how these orbitals form them. So we have two different covalent bonds that are formed. You'll have the sigma kind and the pi kind. Sigma, with the little Greek symbol there, looks like an O, but then instead has a little tail to it as well. So that's going to be the Greek letter S. And then you'll have pi bonds, which you should recognize the little pi symbol probably from your math classes. The way in which the covalent bonds are going to form is going to be in one of these two ways. A sigma bond being that you have a direct, a linear, or if head-on, like two cars coming in. That's an awful example to think about, but that would be a good description of how these guys happen too, is that you have those orbitals coming in at each other just in a direct head-on collision, so to speak, and they overlap one another, thereby allowing them to share their electrons in those orbitals with both atoms at the same time. These kinds of overlaps are found in every kind of covalent bonds, whether it be a single covalent or a double or a triple. The pi bonds, on the other hand, are going to be in another way. It is a parallel overlapping of p orbitals only, and that's going to be used in multiple bonds, so just for the double and the triples. Now, note that I've said that the sigma bonds are in every kind of bond, so that means that in a double bond you're actually going to have sigma and pi's, and in a triple bond it's the same thing. You'll have both sigma and pi bonds. The electrons that are in those p orbitals are going to overlap with one another by staying in their parallel orientation. So in other words, you're not going to have the two p orbitals come in head-on at each other. You're going to come in side by side, sort of like railroad tracks. And interestingly enough, if you remember from the discussion on the hybridization PowerPoint narrated file, that I talked about how that if you hybridize certain orbitals, you'll grab like an S and then a certain number of p orbitals and hybridize them, make a combo out of them, that we were left with, on occasion, we were left with a p orbital that had nothing to do. And I said, well, we're going to do something with him later. Well, here's now that time. Those extra or leftover p orbital electrons that still didn't have a partner, they're going to overlap with other p orbitals in a parallel fashion, forming a pi bond, so that they too will then share their electrons between two atoms. So let's take a very simple example like hydrogen, molecular hydrogen, H2, where you have just a single covalent bond between the two hydrogens. Well, how is it exactly then that the covalent bond forms? Well, it would be such that you have the s orbital electrons from each of the two hydrogens and just squeeze them together head-on, fusing them together. And then that overlap that is between those two orbitals, I'm coloring in red here, that then is going to be that sigma overlap, or that sigma bond, where the electrons are now occupying both orbitals at the same time. It would be as if I could come down here and draw two electrons that will now be spin paired, one up and one down, okay? And by those two s orbitals overlapping, it'll be as if then both of those electrons are occupying both s orbitals at the same time. That's how you get the single covalent bond between the two hydrogens. Well, what they actually do then is those two s orbitals fuse together to form this little jelly bean shaped thing. And that's called a molecular orbital. In other words, the two s orbitals cease to be two separate s orbitals, and they become one, called a sigma molecular orbital. That's really beyond the scope of the course right now, but if you do go on and take organic chemistry next year, you'll definitely start talking about molecular orbitals, and so you'll investigate that later if you need to. If you have sigma orbitals, it doesn't have to be just simply between two s's or even two p's. It can be in a combination. So let's look back at an example that should look familiar to you if you already looked at the geometry and the hybridization tutorials, that you have here a methane molecule, which is CH4, and I have then 4 single covalent bonds between the carbon and each of the 4 hydrogens. Well, that sigma bond, or that covalent, that single covalent bond, is actually going to be a sigma overlap. Well, a sigma overlap between whom? Well, for the carbon, we had determined back in those previous examples that they would form 4 sp3 hybrids. And then what kind of an electron, or where is the orbital for the electron of a hydrogen? Well, it's in an s orbital because its configuration is just 1s2. So that sigma bond is really going to be formed between the s orbital of the hydrogen and overlapping then with an sp3 orbital from the carbon. So you can have a mixture of different orbitals. The sigma part is just saying how they approach one another and overlap. So it's just a direct head-on overlap. So if we look at how that happens, just review real quickly that for hybridization, you are going to be taking that electron and promoting it into an empty p orbital. So you get 4 unpaired electrons. But of course they have to have the same energy, and so we hybridize them by combining then the s and all 3 of the p orbitals to form 4 sp3 hybrids. Again, if you need to review, go back to the hybridization PowerPoint narrated file and take a look again, or in the book too, if it helps, to see how these hybrid orbitals form. So what we'll have then is going to be these green lobes. Those are going to represent my little sp3 hybrids from the carbon, and then the s electron from the hydrogen that are represented by these little gold circles. You'll see then that they directly or head-on overlap with one another in a sigma fashion, and the 2 electrons then, one from the carbon and one from the hydrogen, are now occupying both the sp3 hybrid and the s orbital simultaneously. That's what makes those 2 electrons being shared, which makes our single covalent bond. And so you'll actually have then 4 sigma bonds in this molecule. Oftentimes in the questions like on the homeworks and in the practice tests and on the final and such, we'll be look at a molecule, draw its little structure, and simply count up how many sigma and pi bonds you would have in the molecule. And so here we have a molecule that has 4 sigma bonds. Here's another example just to show you different combinations. Here we have BeCl2. This is similar to a molecule that I had gone through in the geometry exam PowerPoint narration, and how you have some sp hybrids for the beryllium, but then the chlorine, whose configuration ends in 3p5, well, he just needs to share 1 electron. Well, that 1 electron will be in a p orbital, and so here then we have a sigma overlap that is between then the p orbital from the chlorine, but to a hybrid from the beryllium. So again, you can have any kind of a combination of orbitals overlapping, but if they are doing so in a direct head-on overlap, slamming into one another, and then that overlap is called the sigma overlap. So this one has 2 sigma overlaps. For the p orbitals then, we're going to take those p orbitals that still have an electron in them, and if you take another p orbital and then just simply squish them together, you then end up with 2 p orbitals that then make a combined molecular region, or molecular orbital region, both up above and below the axis where the nuclei are. Okay, and so we'll see in other molecule examples here in a second that if you have orbitals that are directly in line with the nuclei, that's where sigma orbitals are taking place, or overlaps. But you will have then the pi bonds, which are described by this direct overlap now of a parallel relationship between the 2 p orbitals. So the electrons are actually occupying a region of space up above and down below 90% of the time, up above and down below the axis where the 2 nuclei are in line with one another, or where any kind of a sigma bond might be taking place. This only counts, though, as just 1 pi overlap. Okay, even though you have a region up above and down below, it's just taking the 2 p orbitals and squishing them together, both up above and down below, but it was only 1 orbital apiece. So this is just going to be called 1 pi bond that is caused by this parallel overlapping of the p orbitals. So let's take a look at where you would get these pi overlaps possible. If you had, say, a carbon atom that only required 3 regions of density, again, this slide should look fairly familiar. It's an example from the previous hybridization PowerPoint. If you had the carbon only needing 3 regions, well then I would grab onto the s and only 2 of the p orbitals to give me then 3 sp2 hybrids. The hybrids are going to be involved in making sigma bonds. Since you have 3 regions, that means that that carbon, or whatever the element is going to be making bonds to 3 different things. And so that's going to be, and or lone pairs, just have to have 3 regions. So that's going to be where the sigma bonds come in, the direct overlaps. But what do I do then about the extra electron that's in a p orbital all left by himself? That is where the pi bond comes in, because that electron then is still in an unhybridized or normal p orbital that will look like the little propellers. So the only way that it would be able to overlap would be with another p orbital, for our purposes, with another p orbital, and make one of these pi overlaps. So let's see some pictures of how this might occur. Take a molecule, this is called ethene, or ethylene. It's used in the making of plastics and all kinds of other things. Let's look at this carbon on the left-hand side here. Well, if I go through and count up the regions of electron density that I have 3 regions of electron density. Remember that I have a single bond that counts as 1 region, I have another single bond here that counts as 1 region, and then I have a double bond, and that only counts as 1 region. Okay? Remember, it doesn't matter, back from the geometry discussion, it doesn't matter whether it's a single, double, or triple, it just counts as 1 region. So that's the 3 regions of electron density. Well, so that means that I would then have sp2 hybrids, can't make my 2 there, sp2 hybrids that will then form the sigma relationships between the orbitals of the hydrogens and the right-handed carbon. So that means that I will have an sp2 overlapping then directly head-on with an s orbital from each of these hydrogens. And since this right-handed carbon is exactly the same as this other one, it's a carbon copy. Get it? Carbon copy? Okay, sorry. I'll have, this is a 3-region carbon over here as well, so it's just coincidence that I've only got an sp2 hybrid there as well. I will then have a sigma relationship that will be between those 2 sp2 hybrids overlapping directly head-on. Well, that accounts for then this having a sigma piece, this being a sigma bond, and this being a sigma bond. But what about the other piece, or the other 2 electrons that make up the double bond? That is going to be then the pi bond, which will be the p orbitals. If I can draw a fancy p orbital there, that is going to be from 2 p orbitals lined up like railroad tracks that will then overlap up above and down below the axis where the sigma bonds are taking place. Okay, that looks like a mess. Let's look at a picture from the book. It would look like this. There's my 2 carbons. Now, they don't have the hydrogens. You could draw in your hydrogens. That's really a bad sphere. You could draw in your s orbitals from the hydrogen, but you would have then that sigma overlap for the electron that's in the s orbital of the hydrogen and the sp2 hybrid. This sigma bond here in the middle, that is an sp2 hybrid overlapping with another sp2 hybrid, one from the right-handed carbon and one from the left-handed carbon. And then up here, then you've got your hydrogens as well. Okay, I won't muck up the drawing here too much here. I'll just leave the hydrogens out like they've done. And then here's those p orbitals that are lined up parallel to one another, and so that is my pi relationship. One of the things that we'll often do with molecules is we'll say, okay, from the Lewis structure, so not seeing visually the pictures of the little orbitals in front of us, just from the Lewis structure, we'll count up what the total number of sigma and pi bonds are for the molecule. So I would have a sigma between this left-handed carbon and the hydrogen up above. That counts as 1. Then I'd have another sigma for the other hydrogen, and I would have a sigma between the 2 carbons. So that's 3 sigmas. Then on the carbon on the right, I would also have another sigma with each of his 2 hydrogens. So that's 1, 2, 3. I'm up to 5. I'm up to 5 sigma bonds, plus then the p orbital. So for this entire molecule, I would have 5 sigma and 1 pi bond between all the different orbitals. Okay, so I'd have 2 sigmas for each of the carbons to their respective hydrogens. That's a total of 4. Plus the sigma bond to one another, because their hybrids are overlapping in the middle here. Okay, then I have the p orbital, or the p orbital from both of the carbons overlapping to form the pi bond. So I would have a total of 5 sigmas and 1 pi. So you just got to sort of remember, I mean, I hate to kind of reduce it to this, but you sort of remember a single bond is 1 sigma, A double bond is 1 sigma and 1 pi. So single bond is just 1 sigma. A double bond is 1 sigma plus 1 pi. And then a triple bond, as we'll see here in a second, is going to be 1 sigma and 2 pi bonds, because we'll have the necessary orbital overlap for a sigma bond, but then we'll have 4 more electrons to go, making a total of 6. That'll be for 2 pi bonds. Here's just another representation of that same ethylene molecule. There you have the sigma overlap between the 2 hybrids in the center. That gives me a sigma bond. And then we've got the p orbitals that make the pi bond, plus all of the sigmas to the carbons and the hydrogens. What if we had 2 regions? We're going to do a molecule here in a second. We'll do like acetylene, which has this Lewis structure. That's a bad carbon. But you have 2 carbons that have a triple bond with one another, and then a single bond to each of some hydrogens. So we'll have only 2 regions. We're only going to have 2 regions around each of those carbons. One for the one from the single bond, and 1 for the triple bond. Okay. When you're counting regions, doesn't matter what kind of a bond it is, just that you have a bond there. So when I hybridize, 2 regions means hybridize the S and just one of the P's. Again, go back to that hybridization PowerPoint if you need to review. That leaves you then with 2 p orbitals all left together by themselves. Well, so I used the px for the hybrid orbital. That means that what I've essentially got is left over a py and a pz. Well, so that we can keep track of what's really going on here, remember that when you see these p orbitals, they are really along each of 3 axes. And so my py is really oriented like that. And then my PZ is coming out of the computer screen right now at you. That's the one that's coming right directly out at you and going back behind the computer screen. So I'm going to have 2 of those p orbitals able to then make overlaps with 2 other p orbitals that will be then just side by side or in a parallel relationship. But as you can tell, then I'm going to have 1 overlap that will be in line with the screen, and then 1 set of p orbitals that are overlapping, but they're really coming out at you. This looks much better with the pictures that the book gives us rather than mine. So here's my carbon, and then here is going to be the sigma bond that is between the 2 carbons, plus then you have the sigma bond between the carbon and each of the hydrogens. And then you've got the py and the pz. So you've got your 2 p orbitals overlapping. These are like those that would be in the plane. They've tried to rotate them a little bit so that you can kind of see them distinctly. And then you've got the PZs. These are the ones that are coming out of the screen right at you. And so it's in front and then back behind the computer screen where the other 2 go. So you actually have 2 pi bonds that are making up this triple bond. So whenever you have 2 atoms bonded by a triple bond, well, one of those is going to be the sigma bond in between, and then you'll have 2 pi bonds that will be for the triple part. Just another representation, getting all of the different sigma bonds out of there, all the electrons. You'd have then the relationship where you have the sigma bonds all directly head-on with one another. Okay, sigma bond here, and sigma bond between the 2 carbons. Okay, so that's a total of 3 sigmas. And then the 2 p orbitals, 2 sets of p orbitals making the pi bonds, then makes this have then 2 pi bonds. So let's go through just some examples. These are the same ones that we had in the geometry video, where we can look at what kinds of overlaps are between each of the orbitals and just look at the Lewis structures so we can learn how to go directly from the Lewis structure to what we need. So if I have HBr, I have just 1 single covalent bond between those 2 guys. That's going to just be a sigma bond. And it would be if we were to draw in all the bubbles, which you don't have to do, all the little orbitals or the bubble shapes. You'd have an s orbital for that hydrogen, and then you would have a p orbital for the bromine. So if I really, in a bad attempt, try to draw this, you would then have the p orbital from the bromine directly head-on overlap with the s orbital from the hydrogen. That would be the sigma overlap that is occurring between the hydrogen and the bromine. Okay? Remember, we don't We're not doing anything with lone pairs. This is all about how the bonds are being formed. So this is going to be an example of a molecule that would have one sigma bond for the entire molecule. And it's just using the atomic orbitals. There's no hybrids here. For an HCN molecule, well, I've got a single bond between the carbon and the hydrogen, so that means that that's going to be a sigma bond. Then I have a triple bond. So that's going to be then a sigma bond, which will take care of 2 electrons, because it will be the overlap then between an sp hybrid from the carbon and an sp hybrid from the nitrogen. But then I've got the other 4 electrons that are being shared between those 2 atoms, the carbon and the nitrogen. That's going to be then 2 pi bonds, because a triple bond is always going to be 1 sigma and 2 pi's. The sigma bond between the carbon and the nitrogen will be an overlap of hybrids. The pi bonds then are again going to be overlaps for p orbitals. So I have a total of then 2 sigma bonds and 2 pi bonds. Boron trihydride, then I would have a boron that is going to hybridize, making sp2 hybrids. They're all single covalent bonds, so everybody being single covalent bonds just means that I've got 3 sigma bonds. I would have those those bonds, the sigma bonds, they would be the overlap between the sp2 hybrid from the boron to the s orbital of the hydrogen. So again, it can be any kind of an overlap between any kind of a combo of orbitals. It's just that because they're head-on in a sigma bond, or in a single covalent bond, they will be sigma. For the ammonia molecule, we have 4 regions of electron density, 3 of which are bonds and 1 which is a lone pair. So we're only concerned about the bonds. So that's going to be a sigma bond that will be the overlap between the sp3 hybrid of the nitrogen with then the it'll be the s orbital. Looks like a dollar sign. Let me just scratch that out. Just the s orbital of the hydrogen. So I have 3 single bonds. That'll equate to then 3 sigma bonds. Water molecule, again, you got 4 regions because you got 2 bonds and 2 lone pairs. But if you're talking about just the overlapping between those things, you'll have a sigma bond. So there it'll be between an sp3 hybrid from the oxygen to an s orbital from the hydrogen. So you'll have 2 sigma bonds. The lone pair electrons, remember, are just occupying hybrid orbitals, but they're not doing any overlapping because they are lone pairs. They're not bonding pairs. Take some more complicated examples. Now, what you'd be expected to do is one similar to bromobenzene, one on the left-hand side, where if you wanted to figure out the total number of sigma and pi bonds in an entire molecule. The example on the right, I'll talk about here in just a second, but a more complicated example like that one is called an organic molecule. It's usually choose molecules that maybe you've heard about in the news, or if you've been in biology or something that you may have a recollection of those. Usually those more complicated molecules, we'll just ask you to count up the number of pi bonds, which equates to just easily going through and saying, okay, let me count wherever I've got a double or a triple bond. And then the sigma bonds are a little more cumbersome because you've got a sigma bond in every covalent bond. That's the singles, the doubles, and the triples. And those are a little bit more tedious. So in a simple example, or a smaller molecule here like bromobenzene, we'd ask you to do both kinds. So let's go ahead and tackle it. In bromobenzene, this is a molecule that you use in organic chemistry. The benzene part, if you've ever heard that word in the news before, you'll know that you've heard that it's a carcinogen, causes cancer. It's kind of a nasty compound. So if you do work with them, you have to take special precautions. But the benzene part here is the part of this molecule that has 6 carbon atoms that are all connected, all bonded to one another in the shape of a ring. And the bonds between the carbons alternate single, double, as you go around the ring. That's an interesting story behind that. I'll have to tell you that some other time. But what I would then have is, in that ring of 6 carbons connected to one another, is I have 3 single bonds and 3 double bonds. So what that would equate to then is 6 total sigma bonds in the ring. And then if I have 3 double bonds, that will equate each of them having one pi bond between the two, because that's what you have in a double bond, is a sigma and a pi. So it'll be a total of 6 sigma bonds, and then the 3 double bonds gives me 3 pi's. But I'm not done. If I want to do this for the whole molecule, well then I've got a single bond between the carbon and the bromine, and then a sigma bond between the carbon and each of the other 5 hydrogens. So that's going to give me another 6 sigma bonds. So for this bromobenzene molecule, what I've really got then is 12 sigma bonds and 3 pi bonds. So you need to be able to do just simple molecules like that, smaller molecules, where you just go through and count up all your single bonds. Those will be your sigmas. And then for your doubles, count it as a sigma bond plus a pi bond for each one. The molecule on the right-hand side, this is Vioxx. You may have heard it in the news, taken off the market. It was an anti-inflammatory used to treat arthritis and things, and just aches and pains and joints and things. Vioxx is an organic molecule, so it's a little bit more complicated than our, table salt and stuff like that. And it's actually written in a shorthand format. You may have even seen these kinds of Lewis structures before, where instead of drawing out the letters, the chemical symbols of every element, that you'll see these shapes that remind you of math class, like these little hexagons. Well, notice that this hexagon here is merely a shorthand for this benzene ring over here. In fact, this guy's got 2 benzene rings. And the organic way of doing it, again, if you go on and take organic chemistry, and we'll do a little introduction to it at the very end of Chemistry 2, or 1120. But if you look at that structure, what you'll find is that in the hexagon shape then, they don't draw in every carbon, so it's a shorthand kind of a notation, and they don't even draw in all the hydrogens. Like, see, there's supposed to be a hydrogen connected to each of those carbons, okay, just like it is over here on the benzene ring. If it's connected to something other than a hydrogen, well, or carbon for that matter, then they actually specify the chemical symbol, like this sulfur. But everywhere else, if you don't see anything specified that's at a corner of a mathematical shape, that really is a carbon. And then if there are any other bonds that need to be made, then those get filled in with hydrogens. Okay? So again, I'm an organic chemist, so that's why I'm very interested in this kind of thing. But what's cool is that if I give you one of these more complicated ones, either on the test or on the final, is could you just go through, and let's not worry about the sigma bonds, just go through and total up how many pi bonds. So it's easy. You just go through the molecule and find all your doubles and your triples and count the number of pi bonds that would be possible. So remember, for a double bond, you'd have 1 sigma and 1 pi bond. So if we were just doing pi bonds, go through here and count up all the double bonds. So I have 3 in this bottom benzene ring. I have 3 in this other benzene ring, so that's 6. I've got a double bond here, so that's 7. I've got a double bond here between a carbon and an oxygen, so that's 8. Then I got a double bond between a sulfur and an oxygen, and then another double bond between a sulfur and oxygen. So I've lost track now. 3, 6, 7, 8, 9. I have a total of 10 pi bonds. Notice each of those double bonds, then they actually consisted also of a sigma bond, but if we just do pi bonds, that's all we need to know. If you wanted to go through and do all the sigma bonds, that'd be a little more tedious to go through, because then you'd have sigma bonds, of course, in every covalent bond in the molecule. So that's including the singles and the doubles. So we'll do some examples like that. You'll see on the practice homeworks and on the practice test for number 4. That you have some bigger sort of like common molecules that you may have encountered in real life, drugs and proteins or amino acids and things, and just count up the number of pi bonds.